Chapter 3, Precipitation and Dissolution. We define the electrolyte or non-electrolyte. Suppose you have a solid substance put in water, you obtain a solution, and if the solid dissociates to electrolytes, dissociates to ions, this solid is called electrolyte. If the dissolution of the solid in the solvent occurs without dissociation to ions, so the solid is non-electrolyte. The electrolyte solute is two types. If the dissolution of the electrolyte in the solvent to ions is complete, so this is called strong electrolyte. And if the dissociation is partial, so this electrolyte is weak. In the case of the strong electrolyte, if you have a certain amount of the sodium chloride that will be dissolved in a certain volume of water, so we cannot ask, or we did not ask, what is the solubility of NaCl in this solution, since NaCl is completely soluble. In the case of the weak electrolyte, for example, AgCl, when dissolved in water, it will dissociate partially to Ag plus and Cl minus. So the question now, what is the amount of AgCl that has been dissociated to ions Ag plus and Cl minus? Or we can ask the question by another way, what is the percent of AgCl that remains precipitated? So in this case, in the case of the weak electrolyte, we can ask the question, what is the dissolution of AgCl to ions, or in other words, what is the solubility of AgCl? So this is the objective of this chapter. Another question, NaCl is composed of cation and anion, and AgCl is composed of cation and anion. So what is the factor that makes NaCl completely soluble and AgCl partially soluble? If you consider NaCl, you have a certain energy that remains Na plus bound to Cl minus. According to the thermodynamics, this is the crystal lattice energy. When you put NaCl in water, you have several types of interactions. You have the attraction Na plus Cl minus, and you have the interaction of NaCl, the positive and the negative pole, with the positive and the negative pole of water. And you know that water has a band structure. The oxygen is more electronegative than hydrogen. So the charge, the partial charge on oxygen is delta minus, that on H is delta plus. So we will have attraction Na plus, O minus, Cl minus, H plus. And also we'll have other interactions between the plus plus and minus minus. So you have several types of interactions. And we explained previously, if the attraction between Na plus and Cl minus is greater than interaction between NaCl and water, so Na plus will remain bound to Cl minus. Since NaCl dissociates completely to ions, that means the interaction between water and the solute NaCl is greater than the interaction between Na plus and Cl minus. So in this case, Na plus will dissociate from Cl minus to give ions. In case of AgCl, since AgCl dissociates partially, so the interaction Ag plus Cl minus is great, and it will overcome the interaction of AgCl with water. In this case, a part of AgCl will be soluble. So what is Ag plus and what is Cl minus? Ag plus is obtained from the dissociation of AgCl. So Ag plus is obtained from the dissolution or the dissociation of AgCl. Cl minus, by the same way, is obtained from the dissolution of AgCl. So Ag plus has one source in the solution, and Cl minus has also one source in the solution, which is the dissolution of AgCl. For this reason, if we know the amount of Ag plus per volume, so we know the concentration of Ag plus at equilibrium, or we know the concentration of Cl minus at equilibrium, and since these two ions has one source, which is the dissolution of AgCl, so concentration of Ag plus equal concentration of Cl minus equal solubility of AgCl. So suppose at T equals 0, if we write the table of conversion according to the number of moles, at T equals 0, we have N0, Ag plus 0, 0. AgCl will dissociate to ions, so it will lose X. At T equilibrium, we have N0 minus X, formation of X and X. X is an indication about the solubility of AgCl that we called later S. So the dissolution of AgCl will continue till the equilibrium. At equilibrium, the concentration of Ag plus or the concentration of Cl minus or the amount of Ag plus per volume or the amount of Cl minus per volume is called the solubility. If we write the table of conversion according to the number of mole, we can put N0, 0, 0 at equilibrium N0 minus X, X, X. If we write the table of conversion according to the concentration, according to the activities, so we don't count AgCl. AgCl is solid. It does not have concentration. At T equals 0, we have 0, 0. At the equilibrium, we have formation of a certain concentration of Ag plus plus X plus X. Pay attention for the written of the table of conversion. If we write according to the number of moles, X is number of moles. And if we write according to the concentration, X is the concentration. Since we don't have at T equals 0 any indications, so if we write the table of conversion according to the concentration, we count only the time of equilibrium. We can put AgCl, give Ag plus Cl minus directly X and X. Since the dissociation occurs till the equilibrium, and the equilibrium is characterized by equilibrium constant capital K, which is equal to the activity of the product divided by activity of the reactant. Since in our course the solutions are diluted, so instead of the activity of the ions, we put the concentrations, and by convention, the activity of the solid is equal to 1. So the concentration of Ag plus at equilibrium is equal to the number of moles X divided by the total volume. That of Cl minus is equal also to X divided by the total volume. K, in case the table of conversion written according to the concentration, capital K equal the concentration of Ag plus at equilibrium times the concentration of Cl minus at equilibrium. So this K is the product of the ions obtained from the dissolution of AgCl at equilibrium. So this K is called the ionic product at equilibrium. The ionic product at equilibrium. But this ion's concentration will define the solubility. So this K is called at equilibrium is called KSP. Solubility as P product and K constant. So this is the solubility product constant. But this never forget that this value KSP is an equilibrium constant. Like for example in the acid base, when HA dissociate to ions to give A minus and H plus, the dissociation will proceed till the equilibrium. So at equilibrium K equal A minus equilibrium times HCO plus equilibrium divided by HA at equilibrium. And since the H plus at equilibrium, the concentration of H plus at equilibrium is an indication about the acidity of the solution, for this reason, we noted K is Ka, the acidity constant. By the same way, the equilibrium constant of the dissolution of weak electrolyte in water is called KSP, the solubility product constant. Also in the acid base, to know that if the acid is strong or weak, okay, we said that according to a value of Ka or pKa between 0 and 14, we can know if this acid is weak or strong. Any electrolyte where we define its KSP, if KSP is given of the electrolyte, that means this electrolyte is weak. If no KSP is given, that means this electrolyte is strong. So we talk about formation of ions by partial dissociation in the case of the weak electrolyte, and the objective is to know what is the concentration of Ag plus in the solution at equilibrium, or what is the concentration of Cl minus in the solution at equilibrium, or what is the percent of AgCl that has been dissociated, or what is the percent of AgCl that remains precipitated. So we talked about solubility in case of the weak electrolyte. What is the solubility? It's the maximum amount of solid in mass or moles that is soluble in a given volume of the solution in liter to prepare a saturated solution. To remember, the solution is several types. We have unsaturated solution. That means we can dissolve more electrolyte in the given volume of the solvent. We have saturated solution. That means we dissolve the maximum amount of the solute in the solvent. We have supersaturated solution. That means we dissolve an excess of the solute in the solution. So the solubility is to calculate the maximum amount, moles or mass, of a certain solute that can be dissolved in a certain or given volume of the solvent to have a saturated solution, to prepare a saturated solution. So the solubility can be expressed by the molar concentration, so this is in mole per liter, or by the mass concentration in a gram per liter. And keep in mind that the solubility is the concentration formed at equilibrium of the ions. So this is X in the equilibrium, or 2X or 3X. It depends on the stoichiometry of the dissociation. For this reason, we replace X by the term S in order to express or to explain that the concentration of this ion formed has one source, which is the dissolution of the weak electrolyte, so it's noted S. You can write it X. So solubility can be expressed in mole per liter or in gram per liter, and you know that the molar concentration is related to the mass concentration. The mass concentration is equal to the molar concentration times the molar mass of the solute. Example, 0.5 a mole of solid substance is dissolved in 200 milliliter of water. Determine the solubility. The solubility is defined by the number of mole dissolved, which is 0.5. Why the number of mole dissolved is 0.5? Since we don't have KSP for this solid substance, that means all the initial solute has been dissolved. So the number of mole dissolved is 0.5 divided by the volume of the solution. The volume of the solution is 200 milliliter of water plus the volume added by the addition of 0.5 mole. But in most cases, when we add solid, we don't change the volume, the total volume. So the total volume is, in this case, 200 milliliter. 0.5 divided by 0.2, the solubility is 2.5 mole per liter. What is the meaning of this value? That means in 1 liter of the solution is dissolved 2.5 mole of the substance A. Another application, 15 grams of solid substance A is dissolved in 300 milliliter of water. Determine the solubility. Since the solid given is its mass, so it's preferred to calculate the solubility in gram per liter. 15 grams of the solid are completely dissolved, since this substance is a strong electrolyte, divided by the volume of the solution, which is 300 milliliter, so equal 5 grams per liter. What is the meaning? In 1 liter of the solution is dissolved 5 grams of the substance A. If the solubility of the saturated solution, this is very important. If the solubility of the saturated solution is 5 grams per liter, what is the meaning of this statement? That means in 1 liter of the solution, we can dissolve maximum 5 grams of the solute. Suppose this is the solubility of the saturated solution. So in 1 liter of the solution, we can dissolve 5 grams maximum of the solute. In other words, if you add 5.1, you will have 5 grams that will be dissolved and 0.1 gram non-dissolved, so the 0.1 gram will precipitate. This is very important notation and you have to pay attention. Example, calculate the solubility of barium sulfate knowing that Ksp equal 1.1 times 10 to the power minus 10. In other words, this is an equilibrium problem. This is an equilibrium problem. You have BaSO4 where K is given. K is given, that means this BaSO4 is a weak electrolyte. What is the meaning of weak electrolyte? Weak electrolyte, BaSO4 will dissociate partially in the solution to ions Ba2 plus and SO4 2 minus. And pay attention for the stoichiometry, 1 BaSO4, 1 Ba2 plus, and 1 SO4 2 minus. As I said previously, it's not necessary to write the table of conversion according to the concentration from T equals 0 to T equilibrium, since directly we can put S and this is S. Why this is S? Since it's 1x and 1x, and x is the solubility. Why we call the concentration of Ba2 plus at equilibrium is the solubility. Since Ba2 plus has one source in the solution, which is the dissolution of BaSO4. Can we write, for example, the solubility is SO4 2 minus? Yes. We can write the solubility is Ba2 plus or the solubility is SO4 2 minus, since Ba2 plus at equilibrium equal SO4 2 minus at equilibrium. So this is the notation. When I write S and S, I means this is at T equilibrium. At equilibrium, any equilibrium is characterized by equilibrium constant K. What is K? K is equal to the concentration of Ba2 plus at equilibrium times the concentration of SO4 2 minus at equilibrium, and this K is called the Ksp. So Ksp equal Ba2 plus SO4 2 minus. It's not necessary to put equilibrium, but keep in mind when you use Ksp, these concentrations are at equilibrium. So it's equal S times S equal 1.1 times 10 to the power 10. So the S, which is, don't forget that S is X, the S is equal radical Ksp equal 1.5 times 10 minus 5 mole per liter. What is the meaning? What is the meaning of this value? If the solution is, when we ask about the solubility, that means of saturated solution. Okay. So what is the meaning of this value? S equal 1.05 10 minus 5 mole per liter. That means in our saturated solution, in 1 liter of the total solution, we can dissolve maximum 1.05 10 minus 5 mole of BaSO4. If you add amount greater than 1.05 10 minus 5 in 1 liter of the solution, that means you will have a precipitation, since you can dissolve maximum 1.05 10 minus 5. Any addition to this value will be precipitated. Another question, What is the KSP of PbI2 if the solubility of the saturated solution is equal 0.00130 molar? We write directly PbI2 solid, give Pb2 plus aqueous, and pay attention for the stoichiometry 2I minus. So at equilibrium we will have X and 2X. So at equilibrium we have S and 2S. This is the concentration of Pb2 plus at equilibrium, and this is the concentration of I minus at equilibrium. So in this case, the solubility is the concentration of Pb2 plus. And if you want to work according to I minus, the solubility is equal to the concentration of I minus at equilibrium divided by 2. Pay attention, the solubility is S. 2S is 2 times solubility. Okay? So the solubility is Pb2 plus at equilibrium, or the solubility is I minus at equilibrium divided by 2. So at equilibrium, we have KSP equal Pb2 plus at equilibrium times I minus at equilibrium to the power 2. So equal S times I minus equal to S. And if you don't want to use S, keep in mind that this is X. So S times 2S to the power 2 equal S times 4S2 equal 4S3. So KSP equal 4. The solubility is given. The solubility is given. This is S equal 0.00130. So the solubility is equal 0.00130 to the power 3, and the solubility equal 8.8 10 minus 9. Keep in mind, this is an equilibrium constant, and the equilibrium constant is unitless.